Okay, so we're going to do a quick round robin to see if questions come through from all the way in the back row and or discussion. So introduce yourself, and we're going to tell Scott he's got to bring donuts one day. So Doug, why don't you tell us what your favorite donut flavor is?
All right, Scott, I like cake donuts.
Any kind of cake, blueberry especially. All right, there we go.
From Seattle.
Oh, even better.
Scott, this is Ethan. I like Boston cream. Scott, this is Clay. I like rollers.
Hey Scott, this is Kevin. I love donuts, but I can't eat them because they may have been in contact with peanuts. So thanks anyway.
Oh, this is good to know. Okay.
Matt, maple.
Matt and maple.
Drew, I like the old fashioned.
The old fashioned.
Yeah.
Oh, like the one actually comes in your coffee?
I think, yeah.
With the handle?
Jason, I like the double chocolate cake dinner.
Ah.
It's got Tommy chocolate covered glaze with the hole.
God, this is Buddy. I like sprinkles.
Sprinkles. Sprinkles on cake or sprinkles on
On donuts.
what? I know, but there's two. There's cake donuts, and then there's there's the breaded kind. The classic. Your oh my gosh. Oh. There's only one kind of donut, and so whether or not we actually hold him accountable for donuts. Now I have a record of what kind of donuts you like, so maybe I will bring them for your last presentation day or something like that. And then we can have the great debate. In Cookeville, it's either Ralph's or Big O's.
See, here it's Donut Palace.
Is it there is only Donut Palace? I mean, there is no other.
There's Krispy Kreme.
Yeah, no.
Duck donuts.
That's like
Duck?
Cards too.
So Donut Palace is actually.
It doesn't matter. It's whatever Scott brings, right?
That's right. Yeah. Okay. So we will proceed with some discussion about because I started reviewing. I haven't marked anybody's comments and/or homeworks up yet, but that's my long weekend joy, is to give you some feedback on that. However, as I'm reading through and looking at your reading comments, it is apparent that there are some flaws in the text. So I thought we might, you share if everybody else has found the same flaws, and has anybody checked to see if there's actually a published errata for the text? Because if not, then as a class, we will write a letter you all can sign, and we'll send it to the publisher and say, look, dude, we found a bunch of errors, and it could be in the typesetter or it could be in the notes, who knows. But Drew, I'm just remembering off the top of my head that you had found one. Do you want to call, or you found two? It was in your reading notes from chapter 6. Yep.
Yeah, and
R squared minus R squared one.
Yeah. 6-3 is those. And 6-18, I think, is also in there.
Yeah, so page 91.
Yeah, on page 91, equation 6-3, instead of being the expected value of R squared minus the expected value of R squared, should be the expected value of R squared minus the expected value of R.
Quantity squared.
Right.
Yeah. Yep. And that actually relates, for reference, back over to equation 5.4,
Right.
which is stated correctly.
Right. What was the other one, Drew? The other one was equation 6-18. They left the square off the B term.
Page 93.
Yeah, the next page.
Has anybody else found anything as you're reading and making notes in the margins, whatnot? When Eric came into the office and we were talking the other day, Eric, you had kind of the scratch your head moment between page 96 and 97, the setting up of the example, and in the middle of the page, the calculation of B11 on B subscript 11 on page 97. Do you want to talk us through what you learned about that?
So my understanding after reading the gum, and you can correct me if I'm wrong, was that what is given to us is not what he says is given to us, basically. So the actual error is the standard deviation, but that includes, I think it includes the coverage factor, which is why they divide by 2. So the dividing by 2 is your coverage factor, and then you square it to give you your variance. That was my understanding.
So I think another way of saying it would be that the stuff you normally get for linearity and stuff is normally confidence intervals, right? Where they're normally given, you have to kind of divide by the coverage factor to get back to the.
Yes.
Right.
Right.
So
Yeah.
this showed up for us like on the chapter 5 homework. We were trying to decide which one he was given to us because he was not very specific.
Mm-mm.
So there was some slack, talking back and forth trying to figure out what it is.
Okay. And that was where I was pointing to, and it's interesting. The author actually comes back when he's talking in chapter 6 on page 101. I don't know if you picked up on the fact there's a paragraph, the actual first paragraph on page 101. Considering the previous example, use measurements from 2 calipers, calculating a length difference. When we evaluated the expanded uncertainty, used K of 2 for confidence interval of 95%. So this K value was used without justification. After the fact, he's explaining why he did it. And therefore, and so that kind of sent me down a little bit of, hey, could we, and I didn't pick up on that in chapter 5. Drew, you said that you had some.
Section 541 is kind of the third on page 83.
Yep.
He talks about if the manufacturer doesn't give you information about the distribution and stuff, but you're probably going to get a confidence interval from them and then how to deal with it. He divides by 2 to 1.96. It was standard deviation.
Yep.
That's where it kind of came up in the 5 homework, which I'm sure what he gave us.
Yep. Yeah. So this idea that it's common to make an assumption, kind of, and so then as Eric and I were looking at the gum document, I got to thinking, well, why don't we all take a deeper look at gum? So today's slide guidance for our conversation is gum, and then NIST, and then NPL. So we're gonna take kind of a guided tour of some resources, and I'm going to encourage you, when you are reading this text, that you are also digging out through ancillary references to try to augment what you're reading. So I'm thinking you may find some value, especially talking about experimental data by looking at the gum. So I'm glad you asked that. It's the guide to the expression of uncertainty in measurement.
So I have a question on what Eric found. You gave us that section of the gum, the 433.
Yes.
So I'm looking at that section, and they have that example where they're doing the weight mass.
Yeah.
And they say that it's,
So I'm gonna go to that so that we can keep that recorded, which takes me out of presentation mode so rapidly. Stop share, and I think that I can then share the PDF, and we can all be looking at the same thing, except I'd already closed the PDF. So, yeah. Don't know if that's the PDF that I have open. Nope. There we go. So now, which one of those is the PDF window? Of course, it's not there because it wasn't open when I went from share. So many different ways to navigate. This one. There we go. Nope, that's good. All gives us a chance to kind of get on the same page. So I had extracted 433, the type B evaluations of standard deviations. So it was there we go. Great.
yep. So the example of calibration,
Yes.
so go to that, it says Certainty value is 240 micrograms
At 3 standard deviation level.
And then it goes on to say when they take that 240 divided by 3, it is 8.
Mm-hmm.
Okay. So they're saying that's not the expanded research or something. It's the again. So that 3 is basically your K. Even though they're saying it's 3 standard deviations, but 3 sigma.
It's 3 sigma, so whatever your sigma point is, you divide by what's here to stand on, you divide by 2.
Right. So because they're stating that your calibration certificate actually gave you that uncertainty is a value at 3 standard deviation. So you explicitly divide by 3. So what I thought was valuable here was then to look at the example in 4.3.4. So you might not necessarily be given a multiple of a standard deviation as the one above. And so I think the takeaway here is in the vagueness, which I'm not really sure that Shaw did on purpose, but it has allowed us to discuss clarity and process. I like this note in the middle of the page. There would be no need for assumptions if uncertainty had been given in accordance with the recommendations of this guide. So in other words, they're being a little snarky right in the middle of it, regarding the reporting of uncertainty, which stress that the coverage factor used is always to be given. So don't leave someone guessing.
I posted a figure.
Yes, you did.
And that's the easiest way for me to figure out what they're talking about. To get back to
The cheat sheet.
the cheat sheet. So whatever they give you, you look at the terminology on the left, you go to the number, you come up, and then you divide by whatever that.
Yeah, so I'm going to, again, to kind of catch this on the recording, so it's good for all of us because we may all at one point want to come back to this at some point. So I'm going to get out of this stop share, and we're going to pull up that diagram, which means that I have to be logged into the class. Bless you. And this would be under discussions. And you posted it under quote, which kind of leads me to think I need to open up another discussion for handy stuff.
Yeah.
Where did I see useful figure? There we go. And I don't know if I can.
Click on the link underneath it.
Yeah.
It's not going to help you.
Well, and I was trying to figure out, because this looks, by the time you kind of zoom it up, and now I'm going to, there we go. So I'm going to zoom it up. But I think there's probably a higher res image out there somewhere. And I'm going to share that particular image. And here we go. So we shall all take a moment to appreciate the diagram.
So divided by 2 when they told you it was 95th percentile is not accurate.
Exactly. So 95th percentile, you should be dividing by
1.73.
so because here's the percentile, the 95th.
The 95th is between the 27th and the 8th, 4.1. So you do the interpolation between the two. So 1.773.
So one could actually print out one of these, and since we could run a line up there and do the 1.73.
So it sort of ties into the coverage factor for you in chapter 5 of 1.9. You're not actually 2, because you're not actually that far out on the top curve.
Right. They're actually like it approaches 1.96. And that actually, yeah.
Is that the one that's percentile goes from C1 to 99?
Yep.
That's a cumulative, so that means below that value on the curve.
Yes.
Is that different than what we're dealing with these where it's also value plus or minus uncertainty? This is
Yeah, well, that's the cumulative percentages is along that line. Okay.
Like for us, we use 95 a lot, so that's what almost lines up with the plus or minus 2 sigma. We get 2.5 that way, and 97.5.
Right, and the 95 is supposed to line up with the stand-line between 8 and 9. That's the stand-line line.
Right there.
It's closer to 96 the way they showed it on the stand-line.
Yep.
But for all intents and purposes, they're almost the same number.
And stanines is not something that I have commonly used.
Yeah, stand-ins are being used a lot on test board. So my kids get their stand-ins back
Oh, okay.
on everything. They also get their Z-scores back.
Yeah, Z-scores I know.
But yeah, I'm starting to see stand-ins with bars and color-coded.
Huh.
So a stand-in of 8 would be considered high mass, 3 would be complete mass. The stand-ins are coming back for some reason. That's a British term.
Yeah. Okay.
So the Z-scores, I have to run the person checks and stuff like this. So that's just kind of the number of standard deviations away. Is that all it is?
Yeah.
Okay.
Yeah. Yeah, it really is. I mean, literally, you can see 1, 2, 3, -1. So Z-scoring, I first was introduced to Z-scoring when multiple readers were being asked to evaluate like 30 proposals. So let's say that I read 30 proposals, Doug reads 30 proposals, Drew reads 30 proposals, and on a weighting of 1 to 10 on 8 different metrics, you know, I go in and I kind of, maybe I read all across 1 to 10, maybe Drew reads everything somewhere in the 6 to 10 range, and Doug reads everything down in the 1 to 4 range. So of the 30 proposals that Doug reads, his numbers are going to come in and they're going to weight differently against mine unless we Z-score it. So we need to ratio against your mean and standard deviation to get your Z-scores for those 30, my Z-scores for my 30, Drew's Z-scores for his 30, and then we do a combination to kind of say who's your top pick, who's my top pick, etc. So it was all done for funding purposes. It is a bias removal, yeah. So I introduce it all the time now to people who say, well, let's, you know, and even then you still need to do like a calibration exercise to kind of, because then we're going to sit there and fight discrepancies between, even after Z-scoring, if mine is incredibly different than your two, and we're trying to figure out like the top 2 people, which one's going to be chosen or something. So
But they're great because people that are all happy, everybody's awesome.
everybody's great.
They're all the Z-score is Z.
Yeah.
And in the end, they don't get a say.
Right. Yeah. So it invites you to use.
Their interval is so small.
Yes.
Yeah.
They don't get a say.
Right. Yeah. So it invites you to, and that's why the calibration exercise is actually important, so that people can kind of understand. Don't be, you're not everybody's friend on this, right? If you're scoring everybody high, you're nobody's friend. There are people in the room who can usually figure out, for advocacy purposes, they're pre-thinking what's going to happen with their Z-score. Yeah. So
That's why I take the outliers out.
yeah, and that's why you do this, you know, 3-way, so everything's read twice, and then if there's discrepancy between those 2 readers, then you bring in a 3rd and sometimes a 4th reader to, and then there's certain people as a facilitator, if you've got 30 readers in the room, you know, there's certain ones that you don't invite to be the 3rd and 4th reader because they're just not, again, they're not using their range well. Anyway, so yeah, this is a helpful diagram. Where did you find it? I mean, I was hoping on a T. Yes, because I went hunting for it to kind of see if we could figure out what the source was. Yeah. Well, I was looking for a higher resolution image, but okay, good. Okay. Okay. All right.
It's probably on Pinterest or something, but yeah.
Oh, yes.
So in a way, it is a quote because it's quoted from somebody else, right? But I'm happy to make another discussion area for people to post useful images, or we can just keep running with our quotes and humor. So I'm going to get out of share mode. Any other discussion on this diagram? And this is all for normal distribution. Okay.
There was a figure that had for the 4 major types
Oh,
of distribution. See who that was, but they had it for the step, uniform distribution.
oh, that would be handy. Yeah,
So,
yeah. Yeah, if you can remember where in
I think it did. Yeah, I was also looking for a higher resolution for the.
Oh, okay.
future first.
Okay, but are we, Kevin, was there anything more you wanted to ask about the 4 points, the examples that I shared via the email that came out of the GUM document?
No.
Okay. Okay. So that was, I'll go back to sharing the PowerPoint. So the GUM, let's see if I can put this back into large scale. Got me thinking, you know, the GUM's a pretty useful document. It's about 140 pages. So I decided, because where I had found it was not the original Bureau International Measures site. So I decided to kind of find the original site so that I could cite it better for you. So there it is. If you want to pull down the GUM, it's completely free. Because my concern when I shared it with Eric, I was like, I don't really know if this is a free document or not. So I'm going to post it in iLearn, but we're going to be cautious about, because I know like the ASME documents, I have to pay $45 for each one of those. Even there's no difference between electronic cost and paper cost. And ISO type documents are often have a charge with them. So I wanted to be a good advocate for honoring copyright with y'all, but apparently the GUM document's free. So if you want to pull it down and have it for your use, there it is. You can click on the PDF right there in the middle of the screen. And there's the hyperlink for it. So when I post this PowerPoint, you'll have all this. Then since I was there and I started looking at it, I was realizing there's these other documents that are down below out of Working Group 1. So there's 2 supplements, Guide to Expression of Uncertainty and Measurement using Monte Carlo methods, propagation of distributions with Monte Carlo. So that's going to line up pretty nicely with the next chapter in Shaw. So when you start to read, when I give you that assignment to start reading chapter 7, I thought you might want to know that the supplement 1 would be a useful place to add some additional thinking. Then there's the things off to the side here. Related articles. There's actually a software, and we're going to see that in one of the next slides, that if you want to play with it, it's a supplement. It lines up exactly with supplements 1 and 2. So again, I thought when you're doing Monte Carlo work, you may want to look and see what their software looks like versus what you're doing with R on your own. And then there is a tutorial, that second bullet point off to the right here. There's a tutorial for metrologists on probabilistic and statistical apparatus underlying the GUM and related documents. And then there's actually a bibliography on uncertainty. So quite a lot of useful stuff off this one web page. In reading one of the JCGM 104, which is right there, this guide to the expression of uncertainty. So this introduction guide, since I'm all about kind of big picture thinking with y'all so that we don't get lost. What?
It's not showing on the Zoom.
It's not showing on the Zoom? Oh dear.
It stays on the.
Okay, thanks for checking.
Our partner actually cares about it.
Yeah. So what do you see right now?
Right now,
So I think the problem
Is it when it goes into presentation mode?
That's
Okay. Well then we'll.
would be
We'll
like,
skip.
You could just share your desktop and you don't have to switch back.
Oh, that's true. I just didn't want to have that. My whole desktop gets a little scary. So I was trying to be a little bit more organized, but yeah.
Being recorded.
Yes. Yeah. So but this works, right? That's coming through. All right. So take a minute to kind of take a gander at that and see what. So we could pull up the whole 104, and there is an earlier. There's 6 figures that come before figure 7, but the GUM uncertainty framework. So if somebody says to you, hey, we want you to follow along the GUM uncertainty framework, you would know which documents to go to. You would know that, in essence, because this is not in the original GUM document. So the one that I've posted in your reference list that you now can actually get yourself. So I thought you may actually want to pull down 104 to go along with 108. So the top left part of the figure, bounded by the broken lines. You're obtaining an estimate Y of the output quantity, capital Y, and your associated standard uncertainty, U parenthetical Y. And the remainder relates to the determination of a coverage interval. So, would you agree that that's kind of what you've been doing? But now you've got kind of the big picture instead of just kind of following along with steps in a document. Replicating it in a homework, trying to get comfortable with it. Now you've got kind of the big picture view.
Have we seen a good explanation of degrees of freedom? Do you feel comfortable with that?
Yeah, I was wondering about that.
I do not.
You do not feel comfortable with degrees of freedom yet? In the light, so I did start kind of reading back to see what Shaw had actually said about it the first time he kind of introduces it over in
Chapter 5.
well, I think it came out in chapter 3 initially.
Dr. Wilson's thinking about mathematics, it was the more degrees of freedom you think you have, the less you have.
So on page 43, estimating population statistics. I think it gets introduced new, being n minus 1 is the number of degrees of freedom. But
So what I get from it is basically, it's kind of a way to adjust for how many samples you actually get, your sample size compared to the population. You know, if you have a sample and somehow you're able to get infinity amount of data, it would be population. But by using that degree of freedom, it gives you that somewhere in that range to account for it.
Another way to look at it in this context is on the front cover. They have a curve in the number of bars you were trying to use to approximate that. So the more you have, the better approximation you get, but the fewer you have, then you subtract 1.
Just because.
Well, you subtract 1 because the minimum you could cover the curve with is 1 bar.
Yeah.
They keep you from getting that asymptotic. What do we have for you? 9,700. It's like no.
yeah, because when you ran that problem, because one of the things I was going to do was a few of you ran the percentages. You and Kevin ran the percentages a little bit differently. You populated, so that one of the homework problems was to run it at 10%, 50%, but you ran more, so that you kind of populated the table out a little bit more. And I can pull that up if we want to talk about that. I forget which problem that was. I did not bring my notes. It
I think
was,
that was one of chapter 5.
I think so too.
Chapter 5, and the first one problem.
So it was problem 5.6, 5.8. Yeah. Calculate coverage factor, assume the relative uncertainties. No.
First
No, it was 5.6, right?
one, we did 6,
5, 8, there.
yeah,
6, 5, 8.
no, Kevin's looking at the output file, so.
Oh, okay. Okay.
Yeah,
Yeah. And if you don't mind, I'll just pop it up on the screen. We can talk about that. So
Class rep, if you get to work with it.
there we go.
Recording.
Okay, we're not sharing right now. Oh, well, that's because I zoomed in on the, there we go. So assessments, assignments. It was homework. I think it's homework 2. And yeah,
So 1% is not actually accurate. Because can't have cover effect. If you think of the number of bars, the coverage factor is how wide the bar has to be.
So if you want to capture 80% of the data, you gotta have 12 coverage factor. 12 will capture 1%.
Yeah, so 94 bars.
right.
Coverage factor. Ideally, the bar intersects the midpoint. So if the amount above the bar and the amount below the bar. And trying to do the curve approximation, you're trying to break it into linear segments. So the coverage factor of 2 is saying, assuming it's linear, and at the midpoint, what's above and what's below cancel each other out.
Scott will be in the dark on this because we're talking, but we're not showing him anything. So, sorry, Scott. Okay.
Some can't see it and say, oh my gosh, that clears everything.
Yeah, it's crystal clear. We can get back to the story at hand here. So let's see.
That will definitely get a final exam.
Yep. Explain degree of freedom on the final exam. Is this helping?
I think so. I'm actually trying to read where I got more confused.
Okay, what page?
I'm not sure. Page 99 is kind of the roundabouts where the Welsh scatter weight.
So there was a discussion in 6. When you're assuming n number of variables, the covariance has to be very, very, very small. Almost negligible. Otherwise, you have to go back and significantly impact your free.
So we're looking at section 6.2, discussion of coverage factors, effective number of degrees of freedom. So again, so I would invite you, as you are making sense of that, to recognize that every time the number 1 reference for anything that Shaw is presenting is the GUM document. So you may want to spend a little bit of time, because the GUM document, I think, does a pretty decent job of providing some examples. It's 140 pages, so it's its own book. In fact, 144 pages probably is about the same length as the Shaw book, minus the appendix. The Shaw book is 174. So I think the GUM document is going to be kind of a friend to kind of keep at hand.
anybody else, did it appear to anyone else that what they're doing is reducing the number of degrees of freedom based off the filter? That was basically what we did.
Mm-hmm.
Do one, two, and this one, two.
So what this kind of led me back to was in the GUM document itself, this section 5 is determining combined standard uncertainties. And it refers to, all I did was just cut and paste this section right here out of that PDF. That's so you could pull up the full PDF and read all of section 5. But whether or not, one of the things that you needed to make sure that you don't lose when we're kind of working through some of these simpler example problems is the fact that the inputs are treated as uncorrelated. So in the event, if they were interdependent or correlated, you need to know what you have to kind of do to properly combine your uncertainties in that point. So the combined standard uncertainty is the positive square root of the combined variance given by equation 10. So equation 10 in the GUM document is referred to as kind of like the law of propagation of uncertainty. And in the GUM document, if you were then to compare this to the Shaw text, I wondered if you could find the correlating equation or the similar equation, this law of propagation of uncertainty as expressed in GUM. Is it the same as what you were doing with the Taylor series, ignoring the higher order terms, only having one partial?
It just represents the partial.
Yeah. Yeah. So it's equation 6.9. As you're building up in the section 6.1, the Taylor series approach. And I've actually seen an argument on, not an argument, I guess a discourse. Oh, no, it's not. I mean, there's a term in 10 that is 6.9. It's the theta. Yeah.
647. Because that one only shows up before the Shaw seems to do it in reverse. He gives you the hard version first, and then he says, "Oh, by the way, if you can, assume they're not correlated, then do the easy version."
Right.
Or does that all, or assume they're correlated to prove it?
Right. It's the same with assume the coverage factor, where you're like, oh, use 1.96, or you can calculate this hard way and you get 1.960001 or something.
I did like the alternative approach here, or the example that you run a test there. That'll give you a factor that's 9.8 minus 5. But it gives you a quick way to determine whether is if you made a good assumption.
Right. Yeah. Right. So you're right, Drew. It's not. I mean, it's not exactly the same. I was just looking at can you track the discussion between the GUM document and Shaw.
So another one of the Shaw does the hard way and then the easy way is like on page 96, and he goes through pages of how to do the thing the hard way, and then he does this direct approach.
Yeah.
References and thing. So that's the one he kind of did in R and your trees was the check. Yeah.
You do the direct approach and then you go back and make sure that matches your S1 too.
So can you do that, or can you just do the direct approach and call it K?
You can do the direct approach as long as it's less than the cutoff criteria. One of the documents is saying do the direct approach if it's less than 2%.
Just ignore it.
Just ignore it.
Yeah.
And I'm like, okay, what's the basis?
But you already did it, right?
Yeah, what's the basis for 2%? It's like,
Right.
Yeah,
Yeah,
we were doing something in our code, and it's like, well, it's in there, just leave it in there.
Right. If you
Then just remove it.
Right.
You go through all the work that is.
Why do it? I mean, like, you have to kind of do it the hard way to check if you could have done it the easy way.
I don't know, if you look at the code he did It's just dividing by the length of the equation. So I would guess, since he was using X, Y, he was using a very simple equation. I would guess that would blow up very quickly with things in the denominator and the square powers. So once again, Charlotte has covered it very quickly.
Mm-hmm.
So I haven't blown that up yet, but I thought on the second one, the homework was pretty good. In the middle, that was one of the things that you started getting powers in your theta, and you started getting other things. I'm like, oh, was that third group over the second?
This one, so when we were working through the homework, we got to the one where it seemed like they thought we were going to have a really easy answer, and we weren't sure if we were overthinking it, but we didn't find a really easy answer. The one about the power and the voltage, because it seems like it, unless I was doing it wrong, it seems like it depends on what the values for the resistance and the.
Kevin and I have been arguing over this.
Oh, okay, all
I
right.
think it's the lowest order of things.
Let me tell you how fun it is to argue with Doug.
We stopped at 11:30. But I think intuitively it's the lowest order.
Well, so I picked some coherent values, like just pick some different powers, and then one of those, you have to know, and I could try different versions of different values, and maybe I was applying the kind of relative uncertainty on it. But it seemed like depending on how I picked it, like it was a one that had a really low resistance or really low current or something, you would have a different one that was the wrong way.
Right. It depends on the mean.
It's because the relationship between the variables and, the relative, the uncertainty for a high value is still going to be way bigger than lower value.
They're giving you a relative uncertainty, which depends on the mean.
Yeah.
And not what the actual.
So if you look at it that way, that's true, but if you hold P constant, and then you just move the other ones.
Well, you need to know at least two of them. So we put P constant, you still need something else there too.
Yeah, and if we use a really high resistance.
Yeah.
B squared over R
Yeah.
diminishes on the covariance, but it doesn't diminish on the B1.
It just seemed kind of weird, because like in the question, he's like, so which one should you pick? Like it, and like it's independent of what those values were, so I wasn't sure if I was,
No, I'm with you, Drew. I thought it did depend on it.
So I thought for a heater, like a resistance heat dissipate power, it would have been 30, B squared over R. Because the resistance is huge, because you're intending to generate heat. So you would be dividing by a very large number. That would then cause you to have a negative theta 2, which would cause it to diminish on the bottom. But that's an assumption that I have very large.
Yeah, and you're holding a P constant at some value. All right, now change P. Right? You're on your other value, change 2.
Well, they'll change proportion.
I did
Just need to
it
think
mattered
three-dimensional
when I
plot of all these.
Actually,
stuff.
I actually have a board in my office right now that has all this swiping.
That's great. So the conversation that we're having right now is the purpose of a problem like this, right?
not that it's
To-
be like that, where it's
yeah.
like, it gives you 90% of
What you need.
feel comfortable with.
Yeah.
The one that I pulled off the internet was the I has a normal uncertainty of plus or minus 5%. B has a normal uncertainty of plus or minus 5%. R has a normal uncertainty of plus or minus 100%.
Oh, wow.
Because R is not constant.
Yeah.
So it's always cycling. Like, that's interesting. In that case, you want to avoid anything that uses R.
Mm-hmm.
Which would be IV.
Yeah.
So, we have those
Well,
answers.
just looking at it was like intuitively just IV instead of, get those squares out of there and you just have your.
I just couldn't come up with a scenario where the middle in I squared R would have been preferred. Unless you had massive voltage variation.
I got something similar where the IV and the third one, we're predicting was sometimes low, and the other one was low. So depending on your values.
Now we're solving like a PE exam question, 6 minutes or less.
Mhm.
And the fourth chance is fun.
So one of the things, because Shaw really kind of just jumps you into the Taylor series, but then tells you ignore the higher order terms, I did want you to be aware of the consequences of doing that. So I thought it would be useful to spend a minute kind of looking at what you see as the law in 10 versus what would happen if you need to consider.
If we use the same example.
Yeah.
And ignore the higher order terms on it. You can't ignore the higher order terms on squared R. Squared example. So you need to take at least the same order as your variable.
Yep. So this invited the consideration of what else is in the GUM document as well. You've got examples of situation where contribution of higher order terms needs to be considered, and so it kind of gave me a thought process of let's look at the examples that are included in the GUM document. There are 6 of them, and they are well presented. Eric, I don't know if you had a chance to look through any of those. Did you get down into the examples when you and I started? Okay. So today we're going to pick who's going to look at which examples and talk us through them as a class on the 11th. That's one of the Thursday sessions. So I will be turning screen control over to you. And we will let you, instead of me talking you through these 6 examples, I want you as groups to take ownership of one of the 6. So we're going to leave one uncovered. I guess I can talk about the 6th one. But do we want to just take it 1, 2, 3, 4, 5 for group 1, 2, 3, 4, 5? And I think the way you're ordered right now is 1, 2, 3, 4, 5. Or if you want to swap with somebody, you can look at yours and then decide if you want to discuss it or give it over to somebody else.
They seem to know. That just means they're going to talk more.
So we could briefly pull up the PDF document and look at short descriptions of them if you want.
So I don't want to speak for Scott, but Scott may want each one.
Yeah, that's what I was thinking might be. So let's I'm going to jump out of this share and switch back over to the PDF. And at some point, maybe I'll probably take your recommendation to get my desktop down to a more manageable size before walking into this space. But yeah, then we'll watch me struggle way too long. So the N-gauge calibration is, it's a fun one to read through. And I think it actually kind of, I think I agree with you. I think Scott would enjoy this one. Eric, do you want to speak on behalf of your teammate?
I'm sure he would love it.
All right, so we're gonna go, we're gonna put H1 here. All right, so the simultaneous resistance and reactance. You've got multiple measurands, output quantities determined simultaneously in the same measurement and correlation of their estimates. So you got random variation in the observations. You got here the data are actually analyzed in 2 different ways, each yielding essentially same numerical values. So this is playing with lots of, we got approach 1 and approach 2. And again, rather than all of us having to kind of get into the nitpicky details, one of you as a group is going to present this to the rest of us and talk us through interesting things that we might want to know. So who would like the simultaneous resistance and reactance?
Do they get worse from here?
Okay, well, let's look at all of them then. All right, so we have calibration of a thermometer. I know, right? So here we're illustrating a use of least squares. So I mean, this is what I do with measurements class all the time, right? But this would be taking it up a notch for my undergraduate class. So linear calibration, parameters, intercept, slope, estimated variances, and covariance. So calibration of a thermometer should be fairly straightforward. Then we have measurement of activity. So this is similar to H2, the simultaneous measurement of resistance and reactance. I was thinking, because I don't do anything with radioactive samples, radon. So who would like this one? I think we have somebody in the room that does this one. I kind of had a.
We're just reading.
Yeah, you are. Yeah, you're just talking. Okay, so who wants this one? You want H4? Oops.
You can leave the blank sign.
And then we have.
I don't remember SNS being mentioned in the.
Then we have analysis of variance. Gets us into ANOVA. A little bit numerical example. So H5. And then we have hardness. Somebody speaking for H3? Who wants H3? You want that one?
I have no preference.
No preference?
Give me H5 if there's no preference.
All right, we'll take H. Or should I take H3 because I lost 2 years of my life on arguing with the defense.
Oh dear. Okay. So this is not going to take you back into a bad place or anything like that, is it? So.
Yeah. Actually, taking this calibration.
How am I filling out the rest of this?
Six. Cook coffee, 6.
Okay.
We need to look at it. That's all great.
I'll do 2. I'll do 2. All right. So my point is here, and I'll go last. So because I'm not on the table. So what we'll do on July 11th. So this gives you a little bit of time. You've got time to kind of read it, think about it, do your Slack conversation about it. You really don't. Think of it as a mini a warm up for your co-presentation on your 3 weeks later, the case study that you pulled out. Because, yeah, you're just talking us through it. Yep. It's just that easy. You know, but one of the things that I actually kind of like about this PDF document is everything is hyperlinked, right? So as you're kind of going into something, they're going to pop you back and forth to other places. So, you know, if you find, when I'm talking kind of like a guided tour of that, just like Eric pulled out, hey, I didn't quite understand how they got from here to here. Am I missing something? Am I having to assume something? I want you to help us by walking through it and making sure you understand all the steps and the examples. And if there are any gaps that you can fill in, or if there are gaps that you want to bring to us as a group for us to talk through, okay, that's where we'll. Oh, we're going to be all virtual on the 11th. Yeah. But he was saying if you want to have technical difficulties with your Zoom at the moment, so.
I didn't hear her say anything about that. I heard her say.
Yeah.
Because we do not have enough time for 5 groups closer to have questions.
No. So, because we have.
Your questions, read your own.
It always takes us about 10 minutes to get going. So if we had 100 and we always stop about maybe 10 minutes early. So 120 minutes minus, we're down to 100 minutes. So at most you have 20 minutes to walk us through your tour. Okay. So it literally is a warm up for your.
Can we maybe either email you or have a place to upload presentation in case we didn't test being able to present? So in case that turns into a
Yes. Yeah. Yeah. Send it to me because then I can share it out where everybody can see it. Yeah.
that'll be our fault.
I could just make it an assignment, couldn't I? We could make that the homework assignment for week 5. Is a PowerPoint presentation of your example.
So that, a week from today.
Yeah. So the 11th, because we're not all together on the 4th. Yeah. So this is week 4. Week 5, this would be the assignment given in week 5 for the following Thursday.
So the week after 4th of Thursday is
It-
due and
Yes. Yeah. And that's a good idea. I'll just put it up there as an assignment and you can upload it. And I can pop them up and share them. Okay.
Case study is the presentation or written report, right?
Yeah, case study is all presentation. Because yeah. Oh, I did the wrong document. Okay, so we got a plan there. So again, what I thought some of you might want to take a look at, whether or not you do it before the end of class or just to know that it's out there. It is Windows based. These GUM software source, the software for measurement of uncertainty evaluation. So, but it's free. You can download it, but it is Windows based. So I didn't use it on my Mac. So obviously I will try it at work, but I thought you might want to take a look at that. It's not a requirement. It's not a course requirement. You got enough going. I just wanted to share it with you. The tutorial for metrologists on probabilistic and statistical apparatus underlying the GUM and related documents. I did go ahead and hyperlink that out if you're kind of curious to take a look at it. That's the tutorial right there. It's a 44-page document, and I don't find it incredibly useful. I read through it. It is very Englishy, the way it's written.
And it requires the engineer to tell you what level of fidelity.
So I'm just going to say don't spend much time there. But I got intrigued by this half of it, the uncertainty machine and NIST, and the fact that the method described in the GUM and the NIST technical note 1297. So this hyperlink down here is, so I actually pulled up and read the NIST technical note 1297, which I also didn't find particularly useful. I like the GUM document better. But this uncertainty machine caught my eye, and I thought you might want to play with that. So there's the technical note. You can pull it down and read it if you want. It's about 40 pages as well. It doesn't really have equations. It seems like it's all words almost. But there it is, the uncertainty machine. So I thought we might just play for a minute with the uncertainty machine. And there is a user manual to the uncertainty machine. And one of my thoughts for you is, and I'm not going to require it, but I'm going to invite you, if you decide to play a little bit, is could you replicate one of the examples out of the text in the uncertainty machine? So all it is just an online software space, and you can actually kind of look at some examples. You can upload some examples. And then when all's said and done, we'll go back to the uncertainty machine. I think I introduced right at the end of class last time, I introduced this measurement good practice guide. This literally would be what if you end up having to work with an intern or something and you want to bring them on board with kind of what it is that you're doing, maybe this is a nice friendly document as a first read. And that led me to kind of like, I told you this is number 11, so I was kind of curious, what are all the good practice guides from the NPL? And so there's there's a web page here that you can pull up the full listing of them. So many of them are more in-depth than this particular document.
Are they all uncertainty related?
There's other topics. So but we could take a look really quick, because you can't read the fine print on that one. So if I have a Safari window open, I guess I could use Safari. Oh, there's my Chrome. So you've got it's very much on, you know, there's the things that kind of caught my eye that I thought I might take a little bit more look at would be you've got a whole one on dimensional metrology. You got one on calipers and micrometers, estimating uncertainty and testing. What?
We're looking at CMM stuff.
Oh, CMM, yeah.
We use lots of them.
Okay.
You guys want the determining airborne radioactive particles in the workplace? Yeah.
Oh, this one?
You want the probing.
There we go. I'd probably want to go back and look at this one at some point.
These are all in Queen's.
They are in the Queen's English, which makes them rather entertaining.
So we lost a bunch of time because we would call it a supervisory circuit. They call it an enunciator circuit. We call it enunciation circuit. They call it an alarm. So lost in Queen's English resulted in opposition.
Underwater noise.
Mm-hmm.
Care and use of
Oh, yeah. Where is that one? Right there, gauge blocks, yes. Yes, yeah. Yeah, no, I can tell you most people don't take good care of their gauge blocks, so. Mechanical tests. Anyway, I hadn't come across this collection before, so I thought, okay, nice. I'm much more familiar with ASNT documents and ISO documents, but the NPL was new for me. I just thought I'd share it with you. So since I've got that window open, I can cut and paste this. Just the fact that NIST made an uncertainty machine, I just thought that was kind of fun.
better than you probably.
Yeah. So it's a software application to evaluate measurement uncertainty associated with an output quantified by measurement in the form. So it's exactly what you could do: number of input quantities. You can decide what your distribution for those input quantities is. You can set the random space here, and you can do your quantity of interest. And of course, they give you some examples to start with, and you might want to look at the manual. But they have a gauge, resistance, a thermal viscosity problem, a voltage, and I think I just loaded the gauge one just out of curiosity. But when you load an example, you don't get any of the narrative to go with it. So I did this right before I kind of came just to kind of look. So, but there you've got the definition of the quantity, output quantity. So You got your alpha, your theta, and then if you run it, where is your, there we go. Real time running. So I didn't know if you might want to play with this a little bit and see how it compares with what you'll be doing. Because you can end up running and downloading things. So you could, it would be like a comparison that you could run against your R work at some point if you want.
Interesting scale
Mm-hmm.
on the left. So there's probability density.
Mm-hmm. We've got the
Download the R data file.
mm-hmm.
What was the MAD quantity on that?
Do what?
MAD quantity, like average standard deviation or median?
MAD. MAD.
That's one way. Well, maximum acceptable deviation.
Oh, maximum.
But that's when you're running Monte Carlo, you're telling you you can't go outside those bounds. I was telling you it ran right up
Mm-hmm.
to the limit, which normally we would fix the bad number.
So you're sure it's not, there's a R function that's median absolute deviation?
It's weird because it says Monte Carlo, so. We work for DOE, we don't have 20 definitions for it.
Yeah, so that's where I was just looking really quick. I hadn't clicked on this one yet on the about, so you can, yeah, so you got the user's manual and then you've got, there is a 2015 document from NIST. It is running on, it's pretty fast for that. But. So I like this. If you feel the need to validate, verify, or reproduce the results from the machine, you can actually, that's got the actual R set of scripts that you can actually have as well. Mm-hmm. Yes. Yes, we can. Yes, we can. We can do this. Yes, we can. But, you know, there it is. No. We didn't specify 34. So it's a calculated.
Read through the user manual, the math is that median absolute deviation.
That just doesn't make any sense to me with 6 of them. So it would make sense on 10 million. Math will always be mutually assured.
So you did say that you found the MAD definition in the user manual?